Good morning. Varun and I are here from Yahoo's network automation team, and we're going to give a technical deep dive of our real-time network telemetry platform, which we've codenamed Panoptes. The key challenge we had to meet when developing Panoptes was scaling our platform's polling and persistence layers. Simply put, we needed to provide real-time telemetry from Yahoo's tens of thousands of network devices to Yahoo's thousands of employees. We hope that if we made this data easy to consume, our fellow engineers who live and breathe this infrastructure every day would create amazing tools with it. And as you'll see later in this talk, we were not disappointed. But before we get into the new platform, let's take a step back and examine some of the issues we had with our legacy network monitoring tools. One of the biggest issues we had was overpolling. Overpolling is when you have two different monitoring systems who query a device for the exact same data. Naturally, this taxes that device's control plane for no reason. The second problem we had was with data accessibility. We couldn't easily correlate data that existed in multiple different systems. And lastly, all of our legacy tools were dependent on SNMP. We wanted our new platform to benefit from modern control plane features like performant REST and netconf APIs, and whatever else might come along in the future. These problems informed many of the design goals we had for Panoptes. Our first design goal was to minimize the effort required to pull different types of devices or a different set of metrics. This flexibility allows us to avoid vendor lock-in and quickly provide new services to our internal customers. Secondly, horizontal scalability was a must given our scale. And of course, horizontal scalability is just increasing scale by adding more hardware. And our last major design goal was to make this data easy to consume through clean and understandable RESTful APIs. And later on in the talk, Varun is going to walk through some example APIs that were built on top of Panoptes' collected data. Panoptes consists of three major subsystems. We have a discovery layer, which enumerates its devices to collect telemetry from. We have a collection layer that issues queries to collect telemetry. And then finally, we have a persistence layer that sends telemetry from our data bus, Kafka, to various data stores. We implemented scalable discovery and polling through a plugin architecture where plugins are simply Python modules. On the other hand, the persistence layer's main unit of work is a group of Python consumer processes which consume data from Kafka and load it into a configurable data store. With this high-level overview in mind, let's look at how Panoptes fits into Yahoo's production network. For the purpose of this talk, we'll consider our global network as a series of data centers, POPs, and pods connected by a backbone network. Within each data center and some POPs and pods, we have our three main Panoptes subsystems, our discovery, polling, and persistence layers. We chose to put a persistence layer in each data center because we wanted telemetry to still be accessible in the event of a network partition. In fact, you would not want to be without telemetry during a catastrophic event like a network partition. Later on in this talk, Varun will discuss the scenario in much more detail. But let's step through each layer in detail now, starting with polling. At the polling layer, we have our polling plugins, a Celery Task queue, which queues polling plugin tasks for execution, and a series of poller hosts, which executes the task. As I mentioned earlier, a polling plugin is a Python module that targets a certain type of device. Within the module's code, we specify how to pull telemetry from that device. Python has emerged as the lingua franca of the network automation world, so we have ample open source libraries to use in our polling plugins, everything from SNMP engines to vendor-specific clients. So plugin scheduling begins at the discovery layer. The discovery layer calls an internal service to enumerate which devices to poll. For service resiliency, we cache this list of devices for 7 days. Again, this allows Panoptes to function in the event the central service is unavailable or down. Once we have our list of devices, we try to find a matching polling plugin by matching that device's metadata with each polling plugin's target information. Then, to actually execute the polling plugin, we place its task on the Celery Task queue and wait for a poller host to fetch and execute that task. Here we see a polling host fetching tasks from Celery, executing those tasks by issuing their commands, and then placing the result onto Kafka for the persistence layer consumer process groups to handle. Now that we've talked about how we poll, let's take a look at what we poll. So Panoptes polls dimensions, counters, and gauges. A dimension is a category expressed as a string. In this example, the dimension is the local address of a BGP adjacency, and the value is the string 1.1.1.1. A counter is a non-negative integer that increases monotonically. An example counter is the number of packets sent by an interface. You can also think of the counter like the odometer in your car. On the other hand, a gauge is a point-in-time measurement that increases or decreases, which is like the rate of packets set on an interface, or going with the car analogy, it's like the speedometer in your car. The goal of our polling layer is to produce a metrics group which consists of these dimensions, counters, and gauges. Then, we place the metrics group onto the Kafka bus for the persistence layer to handle. But before we get to the persistence, let's take a quick look at how we implement our SNMP-based polling plugins. Again, our polling plugins do not have to be written in SNMP. This is just a subset of all the polling plugins we have in our repository. We made extensible SNMP polling by writing an evaluator library that takes a Python dictionary as input and produces a group of metrics as an output. In this example, we specified a target OID, whose value is the local address of a BGP adjacency. Along with the OID, we have metadata that specifies what transformations to apply to this data before putting it into Panoptes. We also say the name that we want to give to this metric and its type, either a dimension, metric, or gauge. Okay, so now that we've made it through discovery and polling, I'm going to hand it off to Varun, who's going to talk about the persistence layer, APIs, and applications that we've built on top of Panoptes. Varun?
Thank you, Matt. So after we've done with polling, we had an epiphany. We actually thought it's going to be, and wait for this, it'll be a breakthrough in the industry if we actually started storing this data. So with that radical industry-changing idea, we decided to use Kafka to distribute the data so that downstream consumers could do untold, unholy, and probably unsafe things with the data that we've produced. Now, one of the things we do with the data is that we convert interface counters in real time to rates, because obviously that's a very common use case in network telemetry. Now, this is interesting since the traditional way of calculating rates has been to actually take a data point, store it, get the next data point, fetch it back, calculate the value difference divided by the time difference, and then come up with a final rate. What we've done instead is that we've made this conversion as part of the pipeline, so that it's available to all downstream consumers. Now, this is similar to the derived data type in collectD or rate in Datadog, for those of you who are into that sort of thing. Of course, we had to solve various scaling problems to do this rate conversion at our data volume. Now, this is a graphical view of what we're doing, what we mean when we say we have multiple consumers. We take the data that we've produced and we currently store it in two places. We store it in a centralized time series database that is available as a service within Yahoo. And we also store an in-colo cache in MySQL. And then, through the rest of these slides, I'll talk about why we actually have an in-colo cache. You would also see that we have a dotted box and line for a future consume. And the example future consumer we've shown here is Druid, which is actually another time series database. But after hearing some of the talks here, maybe we could work with the Sonata team or the Panda team to feed downstream telemetry to, or integrate with them as well. Now, next up, here is an example of the API that we have built on top of the data that we collect. Now, this API is built from the in-colo MySQL cache. The reasons were we obviously don't want the data to be available in case of a network partition that Matt has mentioned, and we also want it to be performant. The thing with time series databases is that they tend to be optimized for storing a large amount of data. They tend to be optimized for being able to run a lot of interesting aggregates against them, but they're not necessarily optimized for speed and returning one data point as fast as possible. And that's a problem we wanted to solve with building a custom API. Now, I know this blurring might remind you of products of the Japanese adult entertainment industry, but it's the best API ever. Okay. Here is what we actually do with that API. We've built custom visualizations. We built custom applications on top of this. This UI is actually used by network operators to troubleshoot things, to answer various questions, and actually even for capacity planning. Here is the view of what happens to the data that we send to us to our centralized telemetry store. The standard use case of sending this data is graphing, which you see up on the screen, and then being able to generate alerts as well. Now, one of the things that Matt had touched upon was what was very important for us was to make sure that we can survive network partitions. Now, when I say a network partition, I'm referring to one of our network sites not being available through the backbone. I'm not referring to a network partition within a network site, not a network partition within a data center. Because obviously, when a network partition happens, we would obviously want to use network telemetry data to be able to troubleshoot why the network partition happened. So the way we solve this problem is by data federation. What happens is that each data center actually knows about the metadata in all other data centers. So you can have a two-step process. In the first step, you can hit any data center and say, hey, I want to get telemetry about this device or various other filtering keys, not just the device name, there's a few others like devices which run this IP version or devices which belong to the site, et cetera, et cetera. It's a find API. And what that site would return you is a response saying that, hey, I don't have the data, but I know this site has the data. The response is a JSON object. And then what the client does is uses the response to follow and connect to the site which actually contains the data. Now, in the normal course of operations, what happens is this is all transparent to our users. The applications that we have and the wrapper libraries they have do this two-step call. And as far as the users are concerned, they ask a question and they get the results back. However, in the case of a network partition, what happens is that our network operators can reach any of these data centers through an out-of-band management network and do local queries. And you will see, like I said, that was the motivation of federating the data and not centralizing it. Now, the data we currently store in each data center is the last point-in-time data in MySQL. And we are considering and looking at using Druid as an in-colo longer-term metric store. So the operators could not only just ask what happened last, but what happened over the period of some time. With that, let's talk about the current status. So Panoptes is being deployed to all our production data centers, and we poll, process, store, index, cache millions of data points per minute. Yahoo service owners actually use the data that we're generating for their day-to-day operations as well as capacity planning. A recent win for the data that we've produced through this platform is that our load balancer operations team was able to use this data to ask how many VIPs have been configured but are not actually being utilized. And the answer was surprisingly a lot. So we were actually able to cut down about 25% of our load balancer resource utilization by analyzing the data that this platform had produced. A few lessons learned. So we knew going with Python would be the path of least resistance, as Matt had said, because it's becoming the choice of development language in the network DevOps world. And Python has delivered. It was easy and actually fun to code in Python, but it's also kind of slow. And the slowness of Python actually becomes glaringly obvious at our scale. Luckily, interacting with underlying C libraries through Python's easy, and we did kind of hand optimize scenarios. For example, we don't use the pure Python implementation of SNMP. We actually use a Python module which wraps the C libraries given by NetSNMP for speed. Another thing that we learned is that creating a lookalike network, which would even remotely mirror the complexity and scale of a production network, was going to be very expensive and time-consuming. So please don't ask me how we solved this problem. And finally, our bet that the best use for data we produce is not simply to feed it into an analysis or a reporting system, but to make it available to engineers has come true. One example of this is we are hammered by requests by teams throughout Yahoo to use our APIs so that they can make it part of their CI/CD pipelines and they can actually look at the real-time state of the network while they're doing automated deployments. And they can take decisions on their deployments based on how the network is doing at that time. Future, this is where I get to be hand-wavy and convince my bosses to fund this forever. So we know that getting high-quality, high-resolution, enriched data is the first step to being able to generate insights. Thus, once we are close to solving the problem of collecting metrics at that scale and at that resolution, the obvious next step is to try and feed this data through machine learning and anomaly detection and possibly even use it for auto-remediation. Also, as Matt pointed out at the start of the presentation, SNMP, though it served our industry quite well, is showing its age. We have already incorporated vendor-specific API-based polling plugins, but one of the next things we want to do is also to support ingesting streaming telemetry from various devices into Panoptes. In terms of coverage within Yahoo, we would be extending Panoptes to poll all the rack switches. This will be an order of magnitude increase in the number of devices we poll, though only about a 3x increase in the number of metrics we generate. And the reason for that is that the current set of devices we poll actually covers a large surface area of Yahoo's network. And then finally, Panoptes would not have existed without open source, and therefore we have a mandate from our leadership to actually open source Panoptes. So hopefully in one of the future NANOGs, Matt and I would be in front of you announcing open sourcing of Panoptes. And finally, it was a big project, and a big shout out to Ian, Sean, Stormy, Sutha, Malcolm, Jess, and Vivek for making this happen. And with that, we will take questions. Wow, we stunned people into silence.
David Hankins, Twitter. As a fellow monitoring developer, I'm more interested in sort of the performance characteristics of the system. What poll cycle you've reached, and sort of maybe the number of devices per core, number of devices per meg of RAM, however you measure that in terms of how you would scale it out. I assume you scale horizontally, so.
Sure, yes. We do scale horizontally. I'll make a few comments about this. One of the things we knew by going with Python is that we were trading off a lot of performance for easier development. So that's something we knew up front. Our criteria to measure scaling is not necessarily devices, because we tend to have devices which produce tons and tons and tons of time series. So for us, a better measurement criteria tends to be the number of time series that we can process simultaneously. In terms of the performance characteristics, maybe I'll talk to you about that offline. I'll have to check if I can even give you the numbers. I will tell you that our key focus, more than scaling performance, was scaling horizontally, if that makes sense. And I'm sure you get why I said that.
That makes total sense. We made exactly the same decision about using Python in the head end for precisely the same reasons. And also, I have merge request number 10 going to NetSNMP to push our version of the C bindings upstream. So
Awesome.
like we're solving those problems in parallel.
Awesome.
So.
Yeah, we use EasySNMP, but we'll look at what you have. A fork of EasySNMP, actually.
Yeah, we tried EasySNMP and PySNMP and I think 6 others, and they all fell down somewhere for us. So,
Yeah. Actually, state of Python SNMP was quite appalling. It was sad to see it. I agree with you. I'm glad you guys are solving that problem.
Tony Tauber, Comcast. So one, issue I think that bedevils a lot of us is you've got legacy tools that expect SNMP polling direct from the routers, and then you've got the new thing that takes it from some data store. And like, how do you, merge it so you can deal with the green field and the brown field and,
Sure.
get a kind of common view of things?
So there's a two-part solution to that. The first thing that we're doing is we're obviously a multi-vendor network. So for any class of device that we poll, we come up with a polling data model. So if we are, for example, polling BGP telemetry, regardless of the platform we do it, we try and do a survey of whatever we use and say, okay, this is the minimum common subset of information I'll be able to get from all my existing devices. And this is what I want, and try and declare a model saying that no matter what device I'm polling, I must produce this information. Today, as of today, that's done by contract, but the plan is to actually sort of try and standardize it. I mean, I think of it as trying to declare, hopefully maybe an industry standard for what the data model of poll telemetry should look like, abstracting away vendor specifics. So that's one part. The other part is integrate. So, on the polling side, no matter what mechanism we use, we normalize to that data model. The other part is we knew that there will be downstream legacy systems we need to feed. And that's where Kafka came in as a choice. One of the examples I'll give you is we depend a lot on MRTG, like I'm sure a lot of us do, and we have a lot of tooling built around MRTG. So we don't want to break any of that while we're migrating to the new system. So one of the plans we have in motion is actually to do the polling through the system, but write out MRTG files. So cut out the polling, which is why polling is persistence is decoupled. So not only will I feed to MySQL, our central telemetry store, possibly an in-core telemetry store, but also write out MRTG files so that I can continue to maintain compatibility with my legacy systems. Does that answer your question?
Yeah, sometimes, easier said than done.
True. Okay, thank you guys.